Welcome to Module 4, Part 3. So, let us discuss the topic of equivalent circuit and frequency limitation. So, to analyze a transistor circuit, it is always necessary one should understand the mathematical model or equivalent circuit of the transistor. So, one of the most important model of the transistor is the small signal equivalent circuit. So, this applies for the transistor which can be used in a linear amplification circuit. So, this is a circuit diagram of a small signal equivalent circuit of JFET. So, it is a n channel JFET. We have the terminals source, drain and the gate terminal. And then we have the resistance RS and RD, the source resistance RS and the drain resistance RD, and the channel in between the source and the drain. The terminals source, drain, gate and the drain terminals. So, this is the equivalent small signal equivalent circuit of the JFET. We have the voltage VG dash S dash. It is the internal gate to source voltage that controls the drain current ID. Then we have the resistance RGS. It is the gate to source diffusion resistance. Then the junction capacitance CGS. Then we have the gate to drain diffusion resistance RGD and the capacitance CGD, that is the gate to source capacitance. RDS is a drain to source diffusion resistance and the capacitance CDS between the drain and the source. RDS is a finite drain to source resistance. So, it is a function of a channel length modulation effect. And CDS capacitance, the drain to source capacitance, is mainly due to drain to source parasitic capacitances. Then we have the drain to substrate capacitance CS and the source resistance RS. We have the drain resistance RD at the drain terminal. So, this is the small signal equivalent circuit of JFET. Now, if you consider that all the diffusion resistance are infinite and the series resistance are 0, so that is the RGS diffusion resistance, RGD and RDS diffusion resistance all are infinite, and the series resistance RS is our series resistances are 0, like the RS, RD and all are 0, and the low frequency, and at low frequency the capacitance becomes open circuit. So, usually at low frequency the capacitance becomes open circuit. Then the small signal equivalent circuit is changed to this particular diagram. So, this is the ideal low frequency equivalent circuit with all the series resistances being 0, diffusion resistances being infinite and the capacitance being open circuit. So, we have the gate to source voltage over here, and then we have the drain current IDS. So, IDS drain current will be equal to GM VGS. So, with all these conditions, the drain current IDS will be equal to GM VGS. So, this diagram is the ideal equivalent circuit which includes the source resistance RS. So, this includes the source resistance RS. So with this diagram A, we can see that the drain current ID is GM/VGS. So the drain current ID equals to GM into VGS. Now we will consider the effect of a series resistance, that is RS. So we need to consider in the diagram B, we need to consider the effect of the series resistance RS. So if we consider the series resistance RS, your IDS, this is IDS, which is equal to GM into VG dash S dash. This is the case when we consider the series resistance. Now the relationship between VGS and VG dash S dash, so that can be found out. VGS equals to VG dash S dash plus GM VG dash S dash into the series resistance RS. So we can take VG dash S dash common, and it will be 1 plus GM RS. So this is your VGS. Now VGS equals to VG dash S dash into 1 plus GM RS. Now with this equation we can write IDS, that is the equation number 1. IDS equals to GM into VGS. So this will be GM divided by 1 plus GM RS into VGS. So this equation can be reduced to GM dash into VGS. Now this is the IDS equation, which is GM dash into VGS. Which is equal to IDS. So this is the effect of a source resistance to reduce the effective transconductance or transistor gain. Thank you.